Good afternoon, ladies and gentlemen. This is Cong Hao from UAUC. This is my great honor to present our work, EDD, Efficient Differentiable DNN Architecture and Implementation Code Search for Embedded AI Solutions. In machine learning development and deployment, there are two very important problems. The first is neural architecture search, short for NAS. It is an automatic neural network search methodology and greatly boosts the quality and accuracy of machine learning algorithms. The second is hardware implementation search. On GPU, TPU, NPU devices, we search for optimized neural network implementations, while on more flexible FPGA devices, we want to search for customized neural network accelerators. For these two very important problems, there is a typical top-down approach. We do NAS first, come up with a well-designed DNN model, and then followed by hardware optimization. Actually, this kind of top-down NAS and hardware implementation approach may result in suboptimal solutions, for example, hardware unfriendly DNNs. To address these drawbacks, one of our earlier work from last year had a discussion that neural architecture and implementation shall be co-searched, called NICE. The idea behind NICE is to propose an automated and simultaneous approach for AI algorithm development and deployment. And in this work, EDD is actually an implementation of the NICE idea. The co-search problem actually contains two different search spaces. The first is neural architecture search space A, and the second is hardware implementation search space I. The key idea behind this co-search problem is that we want to come up with a merged neural architecture and implementation search space A and I. Even better, if we can formulate this merged A and I as differentiable, we can solve it using some elegant approaches, for example, gradient descent. This page shows our proposed co-design formulation. There are three terms in the formulation. The first is the general software accuracy loss. The second is hardware implementation performance loss, for example, latency, energy. And the third is a resource utilization term. Comparing to existing works formulation, the similar part is that we all formulate neural architecture search A as differentiable with respect to loss function. The different part, however, is the implementation part. In the existing works formulation, they are using a fixed implementation I0, while in our proposed formulation, the implementation I is also variable, which can be searched. In addition, we also have an additional resource constraint term. So the challenge here is how can we formulate I also as differentiable with respect to the loss function? This figure shows the overall merged differentiable design space. The first is differentiable neural architecture search space, and the second one is differentiable implementation search. And these two spaces are merged together. Now let me introduce them one by one. This figure explains the differentiable neural architecture search. First, the DNN is built by stacking several basic building blocks. Each block is composed of several candidate operations from OP1 to OPM. In each block, only one operation can be selected. Each candidate operation is a set of DNN layers, for example, convolution, depth-wise convolution, activation, and batch norm. In each block, since only one operation can be selected, this is actually a discrete problem. So in order to convert a discrete problem to a continuous one for differentiable purpose, inspired by this previous work here, we introduced a technology called Gumbo softmax. So here, each operation will be sampled by a sampling parameter, theta, following the Gumbo softmax distribution, and the theta values are differentiable with respect to the loss function. So this is differentiable neural architecture search. This figure explains the idea for differentiable implementation search. We first consider the quantization, which is one of the most important implementation variables that greatly affect both software accuracy and hardware performance. Assume that here each layer can be quantized into either Q1 bit, Q2 bit, or up to Q qubit. This is also a discrete selection, So inspired by the differentiable neural architecture search, we also adopt the Gumbo softmax technique here to search for quantization. Of course, there are way more implementation variables other than quantization. For example, on FPGA, there are parallelism, there are loop tiling and unrolling factors, and on GPU, there are batch size, available resources, and there are other implementation variables that you can think of. So when we want to include these variables, what we need to do is to come up with a differentiable equation under this qubit quantization to describe its impact on performance and resource. So after introducing the differentiable neural architecture search space and implementation search space, let's revisit this overall merged design space. There are 4 stages to come up with entire DNN formulation. The first stage is to formulate the performance and resource for one operation under qubit quantization. Here is an example if we want to include FPGA parallelism as additional implementation variables. In the second stage, we formulate the performance and resource for one operation OP under all the possibilities of different quantizations. As discussed earlier, here we use Gumbo softmax to include all the possibilities. In the third stage, we formulate the performance and resource of one DNN block. Similarly, the Gumbo softmax is also used here. In the last stage 4, we formulate the performance loss and resource for the entire DNN. Let's take a look at the DNN performance first. Actually, we can choose different evaluation metrics for DNN performance, for example, end-to-end latency, throughput, and energy. When we are evaluating the end-to-end latency, it is simply a summation of all the blocks' latency. When we are evaluating the throughput, however, it is determined by the largest latency of all the blocks, and a maximum operation is required and is not differentiable. So this is how we introduced an approximation here. Next is the resource of the entire DNN. The key question here is whether there is or there is not resource sharing between different DNN blocks. When there is no resource sharing, the overall resource is just a summation of all the blocks. When there is resource sharing, actually the same resource that is to be shared shall only be counted once. Therefore, here we introduce the tangent function in order to suppress the maximum expectation of the resource to be shared to be less than 1. So till now, we have introduced the overall flow and how to formulate the merged design space. This is the overall search algorithm. There are 2 essential steps that executed iteratively. In the first step, we fix neural architecture and implementation search variables, and we update DNN weights by minimizing the training loss. In the second step, we fix DNN weights and we update the neural architecture and implementation search variables by minimizing the co-search loss on validation dataset using stochastic gradient descent. And finally, we extract the searched DNN and we retrain them from scratch. Now let me show some experimental results. In this work, we searched for 3 EDD nets targeting different platforms. The first net is searched targeting GPU to minimize latency, the second net is targeting recursive FPGA accelerators, and the third net is targeting pipeline FPGA accelerators. The search is applied on a subset of ImageNet and the test is on the entire ImageNet. Now let's evaluate EDD-Net1, which is searched targeting GPUs to minimize latency. This table clearly shows that EDD-Net1 outperforms all the existing networks regarding latency by up to 2 times speedup, but with very similar accuracy. Second, we evaluate EDD-Net2 searched targeting recursive FPGA accelerators. We evaluate all these networks using Chai-DNN, which is a well-known recursive FPGA accelerator developed by Xilinx. This table also shows that EDD-Net2 achieves the shortest latency on FPGA by up to 1.5 times speedup. Third, We evaluate EDD Net3, which is search targeting pipeline FPGA accelerators. We compare to the state-of-the-art DM builder. This table shows that EDD Net3 achieves 1.4 times higher throughput and also with higher accuracy. Finally, we show the different structures of the three nets searched by EDD, and they look quite different from each other. Finally, we come to the conclusion and future work. In this work, we proposed EDD, a fully simultaneous, efficient, differentiable DNN architecture and the implementation code search methodology. We demonstrated 3 DNN models, and they all deliver similar accuracy as the best existing NAS models, but with better hardware performance. The future works include GPU power and resource formulation and EDD search for dedicated accelerators. This is the end of the presentation, and thank you very much for listening.